few weeks ago, we posted some initial results from our new electrical discharge machining test setup. We could show that different greases produced different responses, but we had lots of unanswered questions. As with the development of all new tests, it takes time for patterns in the data to emerge from which to identify key test parameters. My colleague Cyril Faved has been undertaking the latest work, and his report follows.
Our current tests were run at a load of 900 newtons and with a fixed charging voltage. The bearing is initially running in at 1500 RPM for 5 minutes, with the charging circuit switched off. The circuit is then switched on for 1 minute and the number of discharges counted. This number is compared with the number of pulses applied. With a 2-pole commutator, the maximum number of pulses, hence the nominal discharges, is 2 per revolution. With the charging circuit switched off, the speed is reduced by 100 RPM, and when stable running conditions have been achieved, the 1-minute charge sequence is repeated. The process is then repeated until a final speed of 300 RPM is achieved. The test can then be rerun, if required, in order to assess the effect of accumulated damage on subsequent performance. Otherwise, a new test bearing is used for each test. For the current series, apply voltages of 6, 12, 18 and 24 volts have been used. Data presented here is for a series of tests on 2 greases, Rockwell Sapphire Premier and Kluber Isoflex NBU15. The Rockwell Sapphire did not produce any discharges at an applied voltage of 6 volts. At 12 volts, discharges only start to occur once the rotational speed has been reduced to 600 RPM. At 18 volts supply, discharges start at 1400 RPM, and at 24 volt applied, discharges start at 1500 RPM. It is apparent that once surface damage has occurred, the number of discharges rises very rapidly. At the higher voltages, the discharge rate saturates at the maximum of 2 discharges per revolution. As the speed drops, the charging period progressively increases, allowing the possibility of more than 1 discharge per commutator contact. In this case, extra discharges are observed at the lower end of the speed range. In comparison with the Sapphire grease, the Isoflex grease produces more discharges at the lower charge voltages, but fewer discharges at the higher voltages, with the number of discharges per revolution hardly exceeding 1 per revolution, and then only at the lower speeds. One might conclude that the Isoflex grease produces a more uniform discharge response, in terms of voltage and speed, than the Sapphire grease. The significance of this difference are yet to be established. However, comparing the result bearing damage, the performance of the Isoflex grease appears to be superior. Looking at the data generated when rerunning the test on a previously run bearing, we observe that with the Sapphire grease, with no discharges at the 6 volt charge level in the first run, nothing changes in terms of discharges during the second run, indicating that perhaps no damage had occurred during the first run. However, for the 12 volt rerun, the level of discharges increases significantly, especially at the lower speeds. At higher voltages, the discharge rate simply approaches saturation, 2 discharges per revolution. With the Isoflex grease, the discharge profile is significantly different, with the level of discharge reducing at the 6 volt charging level. Could this be to do with some form of non-conductive additive film formed during the low voltage discharge? At the higher charge voltages, the discharge per revolution remained at a lower than 1 out of a nominal potential 2 per revolution, expect at a very lowest speed of 300 rpm and highest voltage of 24 volts. This current series of tests were run with grade 10 bearing balls. We had previously noted that lower quality balls result in higher discharge levels at lower loads.